and Algebra, and the great scholars that did not see the difference between uh, philosophy and science as being different. So anyway, all right. So enough. All right. So I'm going to go ahead and start the presentation here real quick. So
Sure.
Back it up. And I think I have to change. So, I'm going to apologize in advance because this is not an easy piece of material. I think there's 27 slides, and I barely got through my stuff last time, and now we're at 75. But you can certainly listen to the playback, and I think that Teams now makes a transcript of talks, and so this is probably a good one to be able to pick up from the future there. So I'm going to go ahead and share my screen here and go ahead again. So anyway, deep learning and synapse analytics are not fairly treated without some level of context. There's certainly a lot of stuff in the data warehouse and big data layers that I'm going to be glossing over very significantly. But I have tried to give sort of the summaries, kind of like at the beginning of Game of Thrones, they have episodes of, what happened in the previous episode. And so, hold on to your seats because we're going to be moving really fast, moving on here. So anyway, so the next, so basically, we only got two real topics that I want to talk about. But again, they're pretty broad and deep. And to be fair, even though the title was Azure Synapse, and we will be seeing some Azure Synapse, in action, it's one of those things where I've had a little bit of, we have so much material to cover just to make sure we do due diligence to understand what's actually happening in deep learning that I wanted to make sure that, for people that have tried to peel the onion off, that they had a little bit of understanding of the context here. So I haven't got a chance to put my my Azure Data Science Associate or Data Analyst badges up at this point, but I've had a very storied career. But despite all of my time in corporate America and in startups, I certainly consider my current role in being able to help veterans be able to start a retirement life from the military and be able to learn civilian skills and be able to transform their generational wealth by getting into analytics is a great honor to be able to give back to the people who have sacrificed so much for here. So, again, as I was trying to prepare and trying to look over things that I thought were important, and also just looking at, the big picture, how to help frame deep learning in a context that makes sense to people, I came up with this kind of context that we're looking at here. So we're gonna spend a little more time. We went directly into machine learning from sort of or deep learning from machine learning purist perspective. And we're going to gloss over some of the technical pieces or move them until later and give a little bit of survey of some of the product offerings, because Azure itself is a pretty broad platform with a lot of different places where what we would consider deep learning are available here. And I do characterize there's three deep learning worlds of Azure. I'm not meaning to diss on a fourth that I've added later, but it was kind of a secondary afterthought that I didn't get a chance to update on. And in a lot of ways, it's not really technically a pure Azure play as the other three. So, in general, when we talk about artificial intelligence, it's something that has been the quest of data science and what we've talked about as machine learning previously, as far as anything that can mimic human behavior. And, that can be in simple things where there's a mathematical explanation that can make things that could just speed up the kind of slicing and dicing that you might be able to do in business intelligence products like Power BI these days, or do things that are a little bit more complex than basic ARMA using some type of LSTM machine learning language with the deep learning done. Okay. But these, we'll talk more about these in greater detail here. But just to give a context here, right? Data science is really more getting to the nitty-gritty of understanding the types of manual feature engineering or manual calls to be able to change the raw signal that comes in from the actual data set that we're looking at here. Machine learning is when you're looking at being able to build repeatable models that can be used to train and then apply them there. And then artificial intelligence, the general kind of apps that wrap these pieces around to mimic that kind of behavior. And just for those of you who haven't dealt with machine learning in any depth here, I look at the world that there's a lot of different methodologies. People talk about SEMA, KDD, CRISP-DM, and the Microsoft Team Data Science Process, or TDSP. But I've tried to simplify it there into these type of really cycles of where most data scientists look at the green arrow from left to right as being the primary cycle that they're involved with when we consider machine learning. But it's important to remember that the entire other process of these pieces are going to be not what we're covering, but important to understand the entire cycle in order to understand the consequences of those models here. I like to look at machine learning as the sensory organs for the body corporate, and that you are, what you can articulate ends up triggering their muscle activities and execution. So I chose this, and I'll be going through this a lot quicker for those of you who saw part one here, just to give a basic background of some of the, I used the mnemonic of the 5 families of the Kung Fu tradition to be able to help understand the general categories of machine learning that you run into. So certainly classification is the most common one. We're trying to predict a particular outcome, I guess, no question. It can also be something that has multiple types of answers. Like I've done a machine learning exercise for IHS Markit at one point to look at which of the 219 deep sea ports where oil tankers could fit in the world they would go, because sometimes, especially when prices are volatile, the cargo may change owners 5 or 6 times, so the boats may have a very chaotic route. So it can be a very broad question in those terms. Clustering is really what I like to think about as the statistical lunch tables that data fits in. Sometimes you have hard boundaries, sometimes you have small boundaries. There's a lot of different details going on, but essentially I use the, I call it classification because you're usually having a raw, continuous or decimal number comes out, making a call on with a yes or no, like a line, like a tiger stripe. And then clustering, I chose the dragon because a cluster is a mathematical concept that is useful for describing how it divides and conquers, or can discriminate between one group and another within a data set. And so it's kind of external to the living world itself of the raw signal itself. And then sort of the sister or sibling to classification and traditional loss functions would be an estimation, or what some people call a regression algorithm, where the target of the supervised learning is a continuous value. So I use the spots because there's a wide variety of sizes of spots that you have, and so that helps you kind of understand the actual range to the target of your learning. And then sort of the sister, it's not really related in mammalian terms, but algorithmically, a subset of regressions are when there's an autoregressive aspect, similar to 2 talks ago that we had where you saw an ARMA. With deep learning, there are some fancier algorithms that have come out in the last decade that have made ARMA a little bit more old school from effectiveness. I'm not going to be demonstrating any of the autoregressive stuff, but I certainly recommend looking at Facebook Profit as a library that has some LSTM baked in. And then if you are bold enough to be able to look at building your own algorithms using deep learning, that you look at some of the LSTM algorithms that we talked about. And then finally, the sort of catch-all for anything that doesn't fit into a kind of classical row and table two-dimensional structure, or when you're looking at relationships between those structures as part of the model process. A lot of times it'll be a way to generate features into a supervised learning. It's the sort of bucket for unsupervised and all sorts of things that I associate with the with the crane here. I chose the forecasting because usually when you look at the outputs, like you saw in the talk before last, that you're seeing sort of the path over time where things are going up and down. And I always look at, since you're mostly looking at one kind of feature along this line over time, it kind of reminds me of the snake's path. And then the association, like I said, because there's lots of different birds, they move a lot. They're very dynamic, and it's just a good sort of catch-all. Everything that's fit better in the mnemonic there. So, we'll be talking about this a little bit more as we go in, but the main thing to understand is that the data scientist has a responsibility to use descriptive statistics, tools like Power BI or Matplotlib, Bokeh, Seaborn, what have you, in Python, or R, ggplot, what have you, as far as being able to understand the data well enough to see where there may be distributions of values that can be enhanced analytically to be able to preserve the roots of the signal, but make it a little bit easier for an algorithm to be able to understand the discriminatory aspects. Things like binning, things like log transforms are examples of traditional feature engineering that are done by a data scientist or with a couple lines of code just manually before it gets thrown to an algorithm. Whereas deep learning can use in one actual algorithmic structure a combination of not only feature extraction and actual training to be able to find a pattern that fits to describe in general terms the natural behavior with a minimum amount of error, to be able to get it to something that would be kind of modular as one unit. I liken it to you kind of consume other data scientists' inventions in traditional machine learning of sort of a library with a given import of a package of what machine learning algorithms will use. And when you're doing deep learning, you're really kind of building everything from scratch from traditional building blocks. We'll talk about. So, in other terms, we can look at the core thing that differentiates deep learning from machine learning is the use of neural networks. And, neural networks are not necessarily new themselves. Some people would argue that, having one hidden layer is the same as logistic regression in sort of pre-deep learning terms. And while there's no argument about that, I think that when this is done, you should at least have an understanding of the difference between an all-connected layer in a machine learning, traditional deep learning neural network, or a traditional neural network, or fast forward, and more complex structures. And the way that I try to describe it when I teach students on this is that there's a spectrum of bias and variance. Variance is the difference between the training and the test performance when you do a split on the data. So you're holding out a certain portion of your data to be able to validate that it can repeat the pattern without training on everything that you know. And so, this is sort of I used this slide before, but the main thing is to talk about is that we are building layers is the main concept to look at. And transfer learning is the ability to use when there's a similar data set, things like sound or pictures or words, to be able to use another data scientist's work as a way to be able to add additional nuance that is leverageable for your particular use case and kind of train on top of that layer. And we'll talk more about where that fits into the larger ecosystem of of Azure and deep learning itself. So, to be fair, a lot of time we could talk an entire hour just on any one of these topics, but I want to make sure that you at least have a grounding of where to be in sort of executive terms, how you want to look at the sort of menagerie of deep learning options that are available to you, and so I've tried to clarify them. In addition to be able to try to show you something that's working in Azure Synapse. So, traditionally, I would say that you're really looking at three what I would consider native or Microsoft only platforms that are available. And I'm going to go through these very, very quickly. But the main thing is that Synapse is going to be the main focus, because in a lot of the large scale work that needs to be done, some would argue that that data science, there's a chicken and egg on whether it was data science that led to big data or big data led to data science's revolution. But the idea that you had enough data that was starting to get too big to be able to fit into one machine, ultimately ended up driving a lot of the new innovations that we've seen in the last decade here. So what I've done is that there is this other product that gets confusing sometimes as far as the difference between Azure Databricks and Azure Synapse. And so I wanted to just kind of put in the simplest terms that I can about where things are different and where things are similar. So the core part of the product is, as far as the part that is the most important for why people would use Spark for deep learning, is the combination of having a big data or a Hive support of storage. I use Hive specifically for the SQL aspect of it that we usually see Spark SQL, but also just the HDFS underpinnings of being able to have external tables, managed tables, things like that. To be able to separate compute from storage is a big innovation. So you write once and can throw dynamic numbers of servers at problems depending on what your issue is, and having dedicated hardware is kind of a big revolution. And so both of them can help you there. And I'm not going to go through this list here, but this is more for your homework to try to understand things that are different in the world. We looked at a lot of things in Azure Synapse last time about showing a dedicated SQL pool and some of the innovations that came out of the parallel data warehouse journey, and some of the other innovations that we've seen there. But we spent a lot of time looking at those kind of external pieces, and it's not just to slam Databricks. It's not like it's all bullet points are created equal there. It's just to try to put them into a general category. But you could look at when we're looking at building deep learning work, a lot of the initial bang for your buck training, as far as a person learning how to do it, and people being able to do preliminary work to be able to work out the kinks in what algorithms you may be able to push to a higher scale ecosystem in order to be able to get really heavy duty work done, will come in the Azure Machine Learning Studio. And so this is sort of a full blown set of a lot of different products together that we won't be talking about too much. But to give you an example, one thing that's different about Azure Machine Learning than or when you look at deep learning for Azure versus Azure Machine Learning, is traditionally when you're working with data that's come from a database or some historical activity that you're trying to predict for the future of, you already have an existing target that you're able to use. So, for example, in readmissions for hospitals, you can look back 30, 60, 90 days and see what patients were discharged and, which ones came back within 30 days, and be able to, do outer joins and be able to say, yes, they came back, and no, they didn't, as an example. When you're looking at things like trying to do image detection or trying to build labels on data that's never been really digitized before, and trying to emulate a lot of things like hot dog, no hot dog. You saw that episode of Silicon Valley, what have you. Labeling is a common exercise of being able to add a feature as a target for the machine learning for supervised learning. So you can see that ML-assisted labeling, I borrowed some of the algorithms to say that essentially when it says ML-assisted, it's using a combination of supervised and unsupervised learning to be able to take samples of what you do and then look at a larger pool and make recommendations on which ones it thinks are going to be have similar outcomes or labels to get put on there. But in the bigger picture, and again, like I said, I could spend an hour. I've actually taught whole weeks on just using machine learning, let alone getting the deep learning stuff. But again, there's a large set of complex and repeatable infrastructure that are available within Azure Machine Learning. So I tried to outline here what are the biggest things in the bullet points that are different from Azure Synapse when it comes to the actual deep learning work that you'll be doing, right? You can have an external VM of whatever size you want to build in Azure and be able to throw things from a common Jupyter hub to be able to look at notebooks in there as an example. But again, I don't want to get too far into that part because we have a lot of good stuff in very heavy concepts that I want to talk. So moving right along again, this is a slide that we showed earlier to show sort of the ecosystem specific to Azure Synapse as the primary focus of where a lot of the sort of next generation big data work and the next generation deep learning is expected to happen. This is, again, so these slides are repeats, but just, for those of you who are coming in, it's important to understand that Spark by itself is sort of an in-memory fault-tolerant or resilient distributed data set or RDD-based infrastructure on top of big data that allows you to has many benefits. One of them includes to be able to use streaming, very similar to tables, to be able to have very high performance, low latency querying that can use a combination of static data that's written to disk and data in motion to be able to have a Lambda platform is the way to look at it. But in the scope of what we're looking at, we did a demo where I showed you essentially how you can create an Onyx model in any arbitrary tool that you have. You can even import, you can even take your finished sklearn models or any arbitrarily complex deep learning model and be able to have it converted into an Onyx model and be able to have it imported into Azure Synapse SQL, which is sort of the SQL head of the Hydra of Azure Synapse Analytics that lets that model be applied to data without any data movement out of the, there's no web traffic. It's just all directly on compute on top of the storage you have for Azure Data Lake storage, as an example. When we look at deep learning is something that is a combination of what we always did in machine learning and doing things that are much, much heavier duty as far as the amount of features. If you look at doing a hot encode on even a complex data set like a multi-resolution view of 219 ports and all of the thousands of ships and hundreds of thousands of routes you'd look at, if you break them down to even looking at chessboard and chess pieces at different resolutions, we were only looking at maybe about 500,000 features. And that was something that actually we found was faster to work with in sklearn, random forest, and actually more accurate than using Spark ML-lib, which was the original first generation Spark ML. Now Spark ML has been sort of rewrite of it. But this is an example of a common way of looking at a pipeline built in deep learning to be able to take advantage of doing feature engineering, which is typically something that can be easily scaled out as a map function because you're changing everything on the case level, transforming a picture or updating a row, potentially on some type of aggregate that you're applying on a row like a z-score or what have you. But typically CPU is the best benefit there because those are very small cycles of actual horsepower of memory that needs to be thought of at a time, if you will. And then when it comes to the actual use of the deep learning technologies, GPUs have significantly larger, 1,000 times or more bandwidth of actual memory that can be thought about at, one frame, if you will. Some people look at the architectural bus, the difference between the memory that can be thought about in one set of calculations and applied transforms for weights and work that you do in any algorithmic fitting exercises in a given epoch, comparing it to driving a sports car and then driving a bus as far as the number of people or data that you can fit in, because it's typically look in terms of megabytes for CPUs and gigabytes for GPUs. And then at the end, sort of a lot of times there'll be a flattening or pooling, softmax, what have you, as ways to be able to get to a final outcome that looks like what we did without the complexity of the deep learning algorithms within it. And so, this is another kind of example of why you do, doing things this pipeline on a massive scale is not something that's really available in Azure Machine Learning, but it is something to be aware of. So I would be remiss to not discuss Azure Cognitive Services when we talk about deep learning in Azure, because the reality of the barrier of entry to be able to have a fully functioning deep learning experience is that the amount of training and the level of expertise that is necessary a lot of times to be able to generate a core model that sometimes takes hundreds of thousands of pictures of different things to be able to derive a core expertise on something. While you can certainly learn a lot of the basics and be able to build and understand what's happening inside those, the level of effort of fine tuning and compliance and a lot of the infrastructure that's necessary to be able to do these types of things is something that is it's much more common, and one of the dilemmas to look at when you're architecting solutions is whether you're building from scratch or whether you're buying. And so, I'll talk briefly just about some of the things that you get as far as use cases, and we'll go back as we dig into some of the architectures of deep learning as far as which ones are using what types of modeling frameworks under the covers. And by frameworks, I don't necessarily mean PyTorch or Keras or CNTK is Microsoft's original deep learning innovation work, but more about just the general structures of what types of families of deep learning framework structures of layers. So, natural language processing is the most basic part. And again, I'm not going to read all the slides because, I see that we're getting close to halfway point. I want to make sure that we're not even to the hard part yet of the discussion here. But, for a lot of these basic understanding, you can be able to say, this is a dog, this is a cat, this is good, this is a positive thing that somebody said, this is a negative thing. These are things that are very useful, but, have subtleties like understanding how to detect sarcasm is something that could, waylay a small team for a long time if you're trying to build one of these sentiment analysis for scratch. I would liken the process of building deep learning to much closer to chess than machine learning itself being checkers, because you can get a pretty simple model going with relative ease, but to be able to have all the nuance, to be able to have it be, masterful is something that you want to make sure that you're taking with great consideration before you endeavor it. Natural language understanding is being able to understand the intent of some work. It's still, you could boil it down to some type of complex classification that's being done. Certainly, we'll talk about some fancy models that do things that are much more complex than just having a target of one column that was the target in deep learning there. But it's a way to be able to build a combination of interpretation, application, and also having some actual act that gets to be created. There's another type of machine learning or deep learning. It can be done with both the deep learning or not, called reinforcement learning, where you have agent, you have the usual layer. We talked about the 5 families, but you also have agents and actions and benefit and risk rewards as far as positive and negative. If you've heard of people doing things where they taught, I think Sony's Forza video game, they've recently made an AI that can actually play the game as good as a human. That's kind of a reinforcement thing. We're not really talking about that one today, but there's a little bit of that in the NLU. And then one of the most common scenarios that have a lot of robust things that are baked into being able to have keyword searches that people can plug in to be able to have a topic that's available using an extension of the Power Platform called Power Virtual Agent is a way to be able to have a lot of integration with Power Automate to be able to have a very robust ecosystem of sort of action or reaction to simulate simple conversations. But for complex work, you need to actually have knowledge bases with sort of captures of actual conversations to be able to have machine learning algorithms be able to synthesize more complex conversations in that respect. And there's also speech to text, text to speech as ways to be able to look at the complex signals of sound and turn them into text, and also have them spoken as well. Also translations, recognition as well. So these are huge rows of things where you're not starting from scratch. But again, one scenario I'll talk about is kind of related to this custom insight work. In that I had a student come to me that was at a battery company, and one of the things that they did was there were a lot of custom batteries that had very strange shapes that weren't just you could scan a label at the top and be able to understand, with optical character recognition, what model it was. And so one of the things that they looked at the pilot project for was to be able to take these non-uniform batteries and be able to take three-dimensional pictures of them and be able, or from 3 different angles, and be able to train a model on essentially a classification exercise, multi-class in that case. So you can use, similarly on vision services in Azure, you can look at being able to build these types of complexities here. So there's a lot of cool things that you can do in cognitive services along those lines, and also being able to extract text summarization, or being able to understand answers to questions that are generated algorithmically from being able to digest a corpus or a series of documents is a very common sort of extension of the natural language processing and understanding that you can use as well in cognitive searching. So I'm going to double back on the. I'm going to skip the first demo at this point, because I see we're only at 32 minutes, and I haven't gotten to the hard stuff on the deep dive here. So I want to talk a little bit more about the last topic about buying deep learning before building it, because the reality is that all of these tools have integrations to be able to use things like Azure Key Vault and linked services to be able to have these different platforms work together. So it's not necessarily an either-or solution, but again, there's truly no free lunch when it comes to deep learning, because you're either going to be paying for an expensive service to be able to build that value add of IP on your own modeling, blood, sweat, and tears, or you're going to be bringing a thin layer of your own data and leveraging the collective blood, sweat, and tears of cognitive services along the way, those lines. So just to make sure that your organization is ready for what you have to do, regardless of which one of these combinations of those 4 technologies that you may want to look at, these are the skills you need to look at, right? C# is one that would be much more geared towards using Azure Machine Learning or Azure Synapse, as opposed because Azure Databricks does not support .NET languages at that point. So kind of one thing there. Azure DevOps, again, that's sort of another one. If you're in Azure DevOps, you get a little bit more of a connection with Azure Machine Learning. If you're with GitHub, then your best bang for the buck integration is probably going to be Databricks. But again, it's not just the technical aspect, right? Because it's a sacred duty to be the person that, or the part of the team that is the sensory equipment for an organization, and being able to have your access to the truth before anybody, and then being able to make sure that the essence of that truth is not lost in translation on the pressures of quarterly returns, and making sure that there's ethics that are involved. One thing you have to remember is that there's a lot of responsible AI topics. A lot of those are kind of baked in already into the Azure Cognitive Services as far as how those models were made. So there's been a lot of government regulations to scrutinize them as well. And Azure Machine Learning, as opposed to Synapse or Databricks, also has a lot of these APIs built in for you to be able to integrate with it. So this is kind of one of the reasons you may want to look at one of those. So at the end of the day, before you make these decisions, BYOM being build your own model, right? And like I said, cognitive services may be able to get the low-hanging fruit without you giving any major training in there. But these are the main questions you want to ask yourself. And again, these are not easy questions, but these types of models can make the difference between a company making its quarter or edging out its competition. So these are highly sought after skills and highly sought after outcomes, but they're still created by mortals that usually have to, as some people would say, turn the blood into ink, so to speak. So now we have sort of a picture, a framework of all the sort of breadth of where deep learning may come into play. I want to introduce you to a deeper dive into some of the concepts that we introduced last time. Again, there's going to be a few slides that are going to be review, but as my day job, I'm developing a curriculum for teaching deep learning to people who have never been inside of a math class and were just sort of Python trained from code examples and on-the-job training, so to speak. So I've tried to find the best sort of examples of how to take some of the most complex ideas of deep learning and make them easy for you. And again, it's with that spirit that I introduce the next set of slides. So again, we talked about this one last time, and just to describe a little bit what we're looking at, you could argue that at some level. We'll talk more about what the CONV or the convolution is actually doing, but at many of the levels, there is some type of this activation function that's being used to be able to generate a layer. Some of these may actually be inside, like you can see that there's an example of a residual block of a feedback loop that happens, or a skip that occurs, where there's a in this case, we're seeing to drill in this RALU as one of the layers. But as an example, if you've heard of logistic regression in math class before, or in sklearn, right? That's essentially you can have one hidden layer that's essentially exactly the same as the same type of training that you would do with the traditional sklearn or stats model type of model, and linear would essentially be examples of the types of sort of components that get model together. We're not going to be going through a lot of these basic ones because a lot of times when you're looking at more complex scenarios, you want to understand because you're usually looking at deep learning because the types of things you can do that are easy, low-hanging fruit in sklearn are just not the types of outputs and inputs that you want to be able to look at. And so this is where looking at more complex scenarios makes more sense. And so what I decided to do to make it a little bit more to help sort of the translation from the basic machine learning concepts into deep learning is that I sort of added, a crib note to what are common cell structures, and you could look at essentially at each color layer itself could have one of those activation functions or another type of function that we'll be looking at later, specifically in some scenarios of exactly what is the expectation of what's happening in these scenarios. So for example, you can argue that a feed forward is with one layer is very similar to just a logistic regression or a softmax earlier. Whereas when you get into these recurrent and memory pieces and recurrent neural networks and long short-term memory, that's where you start to have the idea that there's not just one column that you can produce that is the output of what you're actually predicting. So in that case, that's where we start to see the things that are much closer to a human interaction, things like having machine learning based translation. So you're not just looking up into an expert system, that you actually have looked at hundreds, if not thousands or 10,000 documents and be able to translate, 2 words, 3 words, 4 words at a time, and be able to take 2 or 3 words coming in at one level and try to understand forwards and backwards how they work together as a way to be able to add another layer of complexity into how deep learning is different from traditional machine learning exercise. Similarly, a long and short-term memory or an LSTM, the recurrent neural networks, can have a variable output. We'll talk a little bit more about later. But they usually have a pretty fixed set of what they're considering as far as the inputs go. Long short-term memory, it introduces the idea of there being some variability on how many of the pieces it actually uses, depending on, as far as the number of words or the number of pixels, signals for sound that you're looking at there. And, this is, there are other types of algorithms that are, that you may run into. Autoencoding is a very common one where essentially you're getting a different representation of the same data, similar to what you do with the PCA analysis or a clustering. And so a lot of times you may have an encoding and decoding layer that are parts of a transform inside of an algorithm. GAN is pretty interesting stuff. Have you seen things where they generate fake pictures of people? Or I've seen some beautiful things where they fed thousands of different medieval church structures to generate a kind of psychedelic view of a montage of transitions. That's essentially using an idea of replicants and copies and understanding similarities as a way of being able to synthesize the data into a new scenario. So Markov chains are very common to be able to do a lot of work for understanding sort of what are random views of behavior, simple behaviors like micropath analysis or click streams, things of that nature. But when you look at sort of the bigger scenario of what a lot of have evolved as far as the standard of the base structure of this simplest way of understanding how layers get put together. Sequence to sequence is the most, it's kind of this, everything like BERT and Siamese transformers and a lot of things that are getting a lot of attention, particularly in the GPT-3 world, is that under the covers, you're essentially looking at a many-to-many. You could look at a many to, a one-to-many or a many-to-many, many as things that could be in RNN or LSTM scenarios. Sorry, I just realized. Stop the presentation. So that way you can kind of read a little bit further. But what we're going to look at in a little bit deeper context is the very common one that is it's primarily, as far as its outputs are used for classification or regression. So where you have something like saying that this is a dog or this is a bird or this is a car as being a multi-class versus it being a sandwich or bar of soap, what have you. And these are examples of more complex structures of how layers are added to bring in complexity and then to reduce complexity at different phases of the work. And so convolution itself is kind of a weird term. It's one that people banter about a lot of times, but I wanted to spend a little bit of time drilling into convolution networks as a way to kind of help demystify some of the work that goes into building deep learning, so you understand kind of where you're headed when you leave the sort of the sire of row and column, and you embrace not only sparsity but dimensional complexity and flexibility there. So if we look at the most basic scenario of what happens, this is essentially what neural networks look like pre-deep learning, right? Essentially, for each hidden layer, you had to have a connection of all pairs with each of the inputs. So if you have, 100, features coming in, you'd have to have 100 times 99 connections, divided by 2 on each layer, and then have things out. So it becomes, it becomes very complex very quickly. And so a lot of the early uses of neural networks take very long times to train. I mean, I can remember I think we used the basic MNIST data set of, I think it was 16 by 16 pixels, each of them with 255 grayscale of letters to be able to create a simple OCR thing. And I think on the cutting edge, commodity, on a hardware you could buy as just a standalone server, I think it took a couple days in our labs back at Prediction. So, but the question is that if, we may feel like we need to look at those things, but if there's no actual there as far as common relationships between one pixel and another, do we really need to keep that type of that level of detail, because it ends up creating a lot of sparsity that's hard to be able to materialize to build those weights in, and so it ends up being computationally not particularly efficient. And so the question is, can we share these better? So let's kind of drill into we're going to be using as a teaching exercise here for the next piece here, I reset my timer, so if you want to give me like a 10-minute warning there, I'm not sure what our time requirements are, but I at least want to go over, at least have some demo that I've already run that we can just talk about to see what code looks like to do these things. But if we look at the idea of being able to make a beak detector, ultimately in block terms, where we're having a yes, this is a beak, there's a beak in this picture, or no, there's a beak, and we're essentially being able to isolate that it's really just that part of the bird that we care about. We don't really care about wings and feet in general to be able to understand that particular aspect. If you're trying to do something as bird versus dog, you may need multiple of these areas to be able to have an efficient detector. But the idea is that rather than looking at the boiling the ocean and sort of overfitting, overfitting is the wrong term, but sort of over-engineering all the use of the features, it seems like there'd be a simpler way to get it with fewer parameters here. So, here's an example of being able to use something where if we can just isolate based on that picture, what is the part that is that has the beakishness or the birdishness that's most important to us, or multiple locations to have feathers and feet and those types of things that all as the gestalt we can call bird, that we want to essentially divide and conquer in that respect. And so, the idea is to compress this work. So this is where a convolutional layer comes in, because the idea is that what we're doing is we're essentially re-sampling, similar to how you might use binning in traditional histogram work to be able to kind of hide, skewness or kurtotic or multimodal problem by simplifying the actual raw signal into more general terms that looks more like, big, little, and small, so to speak. But, there's a few animations I'll go through to show you like what a convolution looks like under the covers to understand why we have to look at so many different of these layers of different convolutions in order to be able to stack them together to be able to get the type of performance that we want to be able to have these things be extremely accurate and also reusable as a set of features to be able to help us understand what one thing is different from another from the targets. So as an example, there's a concept of a stride, which you can kind of look at as a sampling subset that we're using to be able to generate a new representation of the same data through different areas. So I think I lost a little bit of the alignment because it was supposed to go across the image a little bit more, but basically, actually, let me just rerun this here. Essentially, we're taking small samples of the larger picture and being able to build this convolution layer that is a downsample, right? That we started with a 6x6, and it was all yes or no. And these yes or no's, right, that might be on a red layer, on a green layer, blue layer, what have you, to be able to get a more rich set of ranges of numbers of essentially where there's any signal, but at a more compressed view. One of the mnemonics I saw somebody use is they took a pasta machine and they fed photos into it, and they stripped vertical and horizontal, and then took samples of them to be able to show an example of those filters. For each filter, like really each, green, red, blue, what have you. And so you end up having, two different filters, a 2x4x4 matrix or a tensor that's come out, even though we started with originally sort of a two-dimensional feature set on this layer, but we may do this multiple times. So anyway, so what that does is we've significantly reduced the number of nodes, if you will, in each of the or neurons per layer that then we can then put into a fully connected transformation activation function down the line. So, it's a way of being able to kind of tag team back and forth and be able to use a convolution on the output of that one into another type of model. So what also happens is that, when we have this, since we're looking at an isolated segment, you could represent that that data as a other in linear terms. Like if you remember last session, we took a photo and we did an unroll to be able to take an array of pixels and be able to have one long line of it, because you can essentially say that we're kind of linearizing into a row something that was a region of the picture and say that this is sort of the encoding for a beak, as an example. So, because we're only connecting on the pieces that where there's a filter that makes sense, it significantly reduces the amount of computational complexity per layer, which means you can put more data through it and be able to have a lot of fidelity without a loss of signal. I mean, there are some issues with with vanishing gradients and exploding gradients that you kind of have to manage, but usually with if you throw off layers and different combinations. So what we end up seeing is that there's this alternating scenario of convolutions and the max pool. The max pooling is essentially when we're taking and getting the actual outputs of a simpler representation to be able to have the shared weights there. So here's another example. Let's pull those to the simplest level to the filter. And remember, the subsampling isn't really changing the object, especially because we're striding, so we're seeing several different we're just kind of compressing the data into a different format that still has all the same signal, but it's just easier computationally to handle. For in simpler terms, right, we didn't really lose any birdishness when we went from this many pixels to that many pixels. We just have something that's a little bit easier to chew on. So between the combination of reducing the connections, having the shared weights there, and max pooling, it makes it a lot easier to be able to turn in 2 layers something that's 6 by 6 into a 2 by 2 image. So if that's a red set of pixels, then we have 3 of these channels for each filter, the total. And if we go back to what we were looking at real quick in discussion of activation functions, way back several slides ago, right? We're seeing that there's a convolution layer. We start with 7 by 7, and we do a pool here, and this is a condensed version, right? So then there's a pool at the end, right? But there's essentially expected to be some pools almost at every time you're changing, and this is the combination of the number of pixels and the sort of rollout length that it's end up going to be working with as far as when it considers it's done with the striding. So just to go back to that part there. So, this type of logic makes sense when your data set is a picture, because it's very easy for us to think about this 2, or if you consider RGB channels, maybe an Apple channel, as a 3-dimensional tensor. But it's still something that we could wrap our heads around as being something that we could flatten to X number more columns into a table. And that's not a bad thing. But the good news is that when we think about CNN, we can do a lot more interesting things with it than what you can see in just an image there, for example. So let's talk about flattening for a little bit here. So for example, once you get to the kind of 2 by 2, you can flatten that into 1 by 8, and essentially you've taken a 6 by 6 or 36 different, what would have been 36 different neurons, and you've simplified them down to 8 in just one of those convolution and max pool layer combinations that you've built, as an example. And then you can add, a traditional set of layers to be able to, with that reduced complexity, be able to pull out, a layer where you ultimately have something that would be human readable as, bird or yes or no or whatever the target values for your label, your label that you would use for the supervised exercise. So, it may seem that, for the photo stuff, this is a nice way to look at things, but I want to introduce you to, and again, we're glossing over the agent and reward and action mechanisms, but essentially, if you think about taking this way of being able to simplify a picture as a way to be able to convolute and dual max and then flatten things that can be put into more traditional machine learning scenarios, then it's no surprise when we look at AlphaGo that it took a board and the 19 by 19 locations of where where there are possible pieces and whose pieces were in different places, and then throw them into a neural network and essentially break up entire games as one set of things that ultimately can be described through a regression algorithm as having certain actions. When you move these places, they have these likelihoods of outcomes for games, and be able to build a series of penalty and reward basis on choices made on different configurations of the game. But so neural network as the basic way would have been way too computationally complex cases. But if you think about looking at through a CNN world, it becomes a little bit more practical. And I don't want to go into too much detail on this part here, but they took so 48 feature planes would be a window of 48 positions of the game as a standard case, if you will, for making a decision. Right. So essentially, you could argue it was looking at 48 moves ahead for each decision it was making. So it certainly makes sense that you don't be able to beat humans, because humans don't really think at 48 games, games in a row. But they were able to use the convolutional networks and max pools to ultimately feed into the neural networks that were ultimately driving the agent and the estimations that they're building up for the regressions into a 23 by 23 image there. And getting a kernel size of 5 by 5 extreme. So, like I said, it's, this is a small step forward in a way of being able to breaking up a problem that we didn't have, 12 years ago outside of, the upper echelons of cognitive science and applied mathematics research. But now there's a lot of things that I'm going to be showing you that are kind of the building blocks at state of the art using TensorFlow and Keras that can make this approachable. So another example that I'm not going to be going through in the examples we'll be talking about here is that you can model speech recognition as a way of looking at different frequencies that are happening in sort of fast Fourier decomposition of highs and lows that are in someone speaking, as an example, as a way to be able to identify patterns that can be ultimately labeled to sounds and be able to have that become something that is using an output of a text representation or a phony aspect. And the use of CNN is something that goes beyond just things that we normally think about as being these hard data sets that are less human readable, and how we squeeze our brains into these the boxes that complex data sets like sound and vision do. You can use this type of structure to be able to build, essentially, you could look at a document as a matrix of sentences where each unique word, or in NLP terms, it might be an n-gram of a certain number, an number of n words together, right? As an example, and when you go to google.com and you put in something, you really, if you take out noise words like a and the, prepositions, things like that, if you look at noun and verb, adjective things, they're to trip out on how complex deep learning is in places like Google, they actually use up to 16 distinct noun, verb, adjective, adverb topics, or individual words to be able to create one row in this embedding dimension, at least as far as the raw feature. But again, that's the equivalent of the 1 and the 0 of the 19 by 19 by 48 input that we're putting into these more complex structures. So, this is something that is very relevant, that's kind of under the hood in a lot of the sort of work that comes into what people call word embedding and fancier models. Things like the sequence are still using convolutions and other types of techniques to do this type of feature compression to be able to make them work, but they have a lot of fancier transforms going into the core of the model and transforms going out of them as well. In fact, BERT, if you've heard of BERT, is the bidirectional entity resolution transformers. So you essentially have sort of input and output models on top of the core work you're looking at. So with that, I'm going to go into Azure Machine Learning, and I know we're running a little bit low on time here, but I want to make sure we've at least talked about some things that are worthwhile here. So I'd already run this. I tried to get the GPU working, and GPUs are really important for core work to be able to do things at scale, but to understand how deep learning works on small data sets and simple problems, you can still see the same concepts along these lines. So I'm going to back up here, and we're going to look at a core example. So if we look at that convolution and max pool iteration, this is a visual representation of the code that we're going to be looking at in this notebook here. And this is actually running on Azure Machine Learning Studio, but you can if I get the libraries right, you could also be able to use it on Synapse. In fact, I've already configured, just to kind of show you a little bit of things that we didn't have last time, is that if you create I suspect that ultimately your Spark pools will be supported in other zones, but since these are still in, they kind of just made these out of public beta, or they're still kind of in public beta as far as they're not available in every single zone. But if you build it in the East in the US, then you'll be able to have the option to be able to have GPUs and run the cluster here. But just to give you an example as far as one of the reasons why to choose